let's go ahead and get started then. So, good morning. More people probably show up later. Anyways, so the thing is, I have a lot of announcements for today, but I'm going to send this in an email later, because it's basically going to say, here's when the next quiz is, but that's basically next Friday. And then, let's see, a couple other things, but I think the big thing is that there's still the Zoom office hours link, and then the final extra credit opportunity is going to be mailed out to you guys after my 9:30 class, so just be aware of that. Okay, so just be on the lookout for that. A couple other small things. So other than that, let's start a brand new unit. So we're sort of using what we have from differentiation, sort of talk about a brand new topic, which is basically backwards differentiation. Just the one thing we've been doing this entire semester, been ingraining your head for the past month and a half. Now that you guys remember that, now we're going to do it all backwards because we can. Also because it's super important for some useful applications. There we go. Okay. Focus. Oh, all right. So antiderivatives and indefinite integration. So consider the equation capital F prime of x equals little f of x. So there are two ways to interpret this. So the first way that you guys have seen basically up until this point is that little f of x, so little f of x is the derivative of big f of x. Okay, so that's the first way. But the second way of thinking about it is sort of backwards. So capital F of x is what's known as an antiderivative. Derivative of little f of x. Okay? And the notation for this is written capital F of x equals, so we're going to have this curly S looking thing. It looks something like this. And then little f of x dx. Okay. So that's the two ways to interpret this equation here. So the thing is that with derivatives, we start with capital F of x and then get to little f of x. But with an antiderivative, as you might have guessed, we do the opposite. We start with little f of x, and then we move our way to find big f of x. So with antiderivatives starts with little f of x and find big f of x. Okay. So like I said, this is basically just reverse differentiation. Okay. So to give you an idea what I mean by this, let's take a look at example 1. So if we have big f of x equals x squared plus 2, then if we differentiate this, then so if we differentiate this, we should get the derivative, which is 1, 2, 3, 2x. Good. So nothing too crazy there. But now part B, now let's take a look at what this says. So what this says is that we're trying to say, all right, what this says is that we're trying to figure out what function has 2x as its derivative. So let me write that down. So what function big f of x has 2x as its derivative? Okay. So based off the reasoning that we had in part A, what's one function that you can think of that satisfies this? Yeah, just x squared, right? So x squared, right? Because if you differentiate x squared, you get 2x, which is one way you can express this. So x squared is one such function. One such function, big F of x. But so are the following. So we know that we say, all right, we have x squared plus 2 is another such function, because if we differentiate it, we get 2x. So we have x squared plus 2 is one such other function. But here's the thing. By similar reasoning, so is x squared minus 1,234, right? Or, x squared plus pi to the power of e squared over 42. I don't know, I literally made that up. But point is, you can think of any function that satisfies this as x squared plus any constant, right? That's the idea I'm trying to get at. So x squared plus constants. I'm going to move this last thing. The sun's starting to get in my eyes. That's not annoying. That's better. That's much better. Okay. So, and the reasoning is because, the derivative of any constant is this big fat 0, so whatever constant we have goes away with differentiation. So since derivative of constants is 0. Okay? So to account for this, what we're going to do is to use capital C as an arbitrary constant. Arbitrary constants. So that says the integral of 2x dx is equal to x squared plus c. Okay, so what this tells us is that we have that x squared plus c. This denotes what's known as the general antiderivative slash indefinite integral of 2x, whereas x squared plus x plus any explicit constants is just an antiderivative. Okay. So as an example, so we have x squared plus c as the arbitrary constant is the general antiderivative, whereas these guys up here are with explicit constants. We have that these are just explicit antiderivatives. Those are just one examples of antiderivatives. So, in general, we have that the integral of f of x dx is equal to capital F of x plus c. Okay? And I'm going to say this now because I know people are going to forget this. I'm going to put this in all caps to make sure you remember it. So never forget plus c. Okay? That's super important because that's if you forget the plus c, you're going to mess a lot of things up. So just remember that when you're doing antiderivatives in general. Okay. So, any questions on any of that before we move on, or? Okay. Okay. Does anyone still need this? Okay. Okay. So moving on. So you might think, all right, well, that's great and all, but x squared is just one function. How do we get antiderivatives of other functions? Well, the good news is that since anti-differentiation is basically just reverse differentiation, all we have to do is take some of the derivatives rules we already know and use them to get our antiderivatives. So to answer this question, we get these antiderivative rules from derivative rules. Okay? All right. So let's use this reasoning to get the antiderivative power rule. Okay? So let's think of it like this. So if you guys recall, the derivative power rule says that if we differentiate x to the n plus 1, then what is that going to equal? Kind of, but I think you have n here instead of n plus 1. Yep, just n plus 1 times x to the n. Remember, so you just take this power, you throw it outside as the constant, and then you subtract 1. So I'm writing it this way because that actually will lead us to our antiderivative power rule. So what that means is that, all right, so since we have that the derivative of x to the n plus 1 is n plus 1 times x to the n, then by the reasoning we just established, that means that the antiderivative of n plus 1 times x to the n dx equals x to the n plus 1 plus c. Okay? Okay. So as a result of this, what that says is, all right, so if we were to divide both sides by n plus 1, then what you'll notice is that since n plus 1 is a constant, one nice thing we'll establish in a bit is that we can actually just throw this constant outside the integral. So as a result of this, we say, all right, we have x to the n dx is then equal to x to the n plus 1 plus c all over n plus 1. Okay? So the reason I did this is because then we can say, all right, so let's go ahead and split off these two terms since they both have common denominators. So we have x to the n plus 1 over n plus 1 plus c over n plus 1. So now you might think, all right, well that's good and all, but how do we simplify this further? Well, the good news is that like I said before, c is just an arbitrary constant, right? So c is arbitrary. So as a result of this, what it can do is say, all right, if it's an arbitrary constant, then you can think of c as being able to quote-unquote absorb this n plus 1 factor downstairs. So quote-unquote absorbs 1 over n plus 1. Okay? So what that tells us is that we have x to the n plus 1 over n plus 1 plus c. So then, as a result of it, at the end of the day, we have the antiderivative power rule is the following. So we have x to the n dx equals x to the n plus 1 over n plus 1 plus c. Okay? So you might think, all right, well that's good and all, but one thing to keep in mind is that this antiderivative power rule holds for all n except for what? If we take a look at the with how the antiderivative power rule is established. That says this can hold for any n except for what value? -1, right? So n cannot equal -1 because otherwise n plus 1 equals 0, and we have a divide by 0 error. Okay? So you might think, all right, well, what's the n equals -1 case? Well, we're going to get to that in a bit. But for now, let's talk about some other antiderivative rules. So let's take a look at this, for instance. So if we have, say, f of x plus or minus g of x, and if we want to differentiate this thing, if you recall, that says, all right, well, f prime of x, that's equal to f prime of x plus or minus g prime of x, right? That's basically the property that lets us do term-by-term differentiation. So the similar result of this should be, all right, well, the way to express this with an antiderivative is, well, f prime of x plus or minus g prime of x dx. So if we view this as the derivative and this as your sort of capital F of x, so this would be f of x, and this would be sort of your derivative of f prime. You can view this as f of x plus or minus g of x plus c. Okay? So what's nice about this formula is that this allows us to do term-by-term integration. So term by term integration. Okay. So that's one nice property. So the next one is that if we have b, a constant, okay, what we can say is that, all right, we have b times f of x prime is then equal to b times f of prime of x. So we then say, all right, well, so then we could say, all right, that's b times f prime of x dx. So that's the same thing as saying, all right, well, that's b times f of x plus c. Or if you prefer, we can also write this as equals b times the integral of f prime of x dx. Now, the reason this is so important is because that allows us to say, all right, if we have a constant out here and we want to figure out the antiderivative of a function, it suffices to throw the constant outside the integral to be able to focus on just the integral itself. Okay? Okay, and then just a couple more. So if we have sine of x, focusing on more explicit functions now, if you recall, this is just cosine of x, right? So by this reasoning, what should that tell us? So that says that the integral of cosine of x dx, using the reasoning that we've already established, is equal to what? Go ahead.
Sine
Yeah, it would be sine of x
plus c.
plus c, right? Remember, never forget plus c. Okay? So then again, using the same reasoning for cosine of x, derivative of that is equal to sine of x. How can we express this in integral form? So we say, all right, this is just sine of x. The integral of sine of x dx is then equal to what? Oh, wait, sorry, this is negative sine. Sorry, my bad. Yep, negative cosine x. Right. Plus c, right? Okay. And then from there you get the idea. So I'll say and so on. Okay? And the reason I say this is because if we take a look at the table below, that basically gives us the rest of our derivative rules that we might need. So for instance, if we have, say, derivative of tangent is secant squared, that means the integral of secant squared is tangent of x plus c. And, and the other one that we sort of ignored earlier, but we'll bring up now, is this one right here. So we have that the derivative of natural log is 1 over x, right? But remember, the domain of natural log of x is x greater than 0, right? So to account for this with the integral of 1 over x, we have to have the natural log of the absolute value of x to accommodate for that. Because it's possible that for 1 over x, we could be integrating over an interval with negative numbers in it. So we have to account for that by including this absolute value here. Okay? But the integrating over a negative interval, we'll get into that in a later lesson. But just to give you an idea of why should we have this absolute value here. So. Okay. So any questions on any of that? So one thing to keep in mind is that if you're following along in a notebook, which looks like all of you are, I think it looks like all of you are, which is fine. What I'll do for now is I'll just say, okay, I'll sort of have this sort of on the side, just so you guys can look at it for now. But this is also going to be something in the notes I'm going to post later. But one thing to keep in mind is that this chart will not be provided on an exam. So if you want to reference it later, you can, but just so you guys are aware, it's not going to be something that the exam actually provides. So it's good to memorize it by doing a bunch of practice problems. So with that in mind, let's go ahead and look at the next page with the examples. So what I'm going to do is I'm just going to say, all right, let's focus on example 2. So what we have here is that we have to evaluate the following indefinite integrals. So for part A, we have x to the e plus e to the x plus e times x plus e, and then all with respect to x. So what this says is that we're essentially, because of this dx here, one thing to keep in mind with this dx is that this means that we're integrating with respect to x. So dx equal implies integrate with respect, I'll spell it out, with respect to x. Okay. So one thing to keep in mind here is that for this one, what we notice here is that we have a bunch of terms added together here. So what we can do is say, all right, well, let's go ahead and take a look at one of the rules that helps us look at this. So if you recall, we have this equation here which lets us do term by term integration. So as a result of this, we can say, all right, this integral here is equal to x to the e times of dx plus e to the x dx plus the integral of e times x dx plus the integral of e dx. Okay? So now that means, all right, now we have to focus on each of these integrals individually. But before we do that, one thing we notice here is that, all right, well, if we take a look at this formula here, we say, all right, what this lets us do is say, all right, are there any of these integrals here have a constant floating around? So what that means is that, all right, if we have the constant times some function we know how to have the antiderivative of, then maybe that can help. Maybe we should get rid of that first. So if we take a look, we have x to the e, well, no constants, so don't worry about it, plus e to the x, nothing there, plus e times x, oh wait a minute, we have this constant e which can be thrown outside, so this says that this is just x to the e dx plus integral of ex dx plus, so we can throw this e outside, so we have e times the integral of x dx and plus e times dx. So what this allows us to do is say, all right, now let's go ahead and look at the derivative rules we already have. So for these explicit ones, we say, all right, well, we have x to the e here, which says, all right, so that's just x to some constant, in this case e. So in this case, that seems like we're going to need to apply the antiderivative power rule here. So we take a look at this, we say, all right, this is just, well, x to the, well, in this case, e. So in this case, we just replace n with e. So we have x to the e plus 1 over e plus 1. So that's the first term. Now the second term, if you take a look at the table we've established, the integral of e to the x dx, well, what do you think that's, first off, what do you think this is going to equal given that the derivative of e to the x is just e to the x? Yep, it's just e to the x, right? Because in this case, you're trying to say, all right, what function has e to the x as its derivative? Well, e to the x, so that's all you need. So in this case, that gives you that, and now we have e times the integral of x dx, which seems like we're going to need to apply our antiderivative power rule again. So in this case, if we apply the antiderivative power rule with this integral here, what do you think we're going to get? X squared over 2, right? Because we have, in this case, this is just 1. So all we have to do is just let n equal 1 in our formula here to get, in this case, x squared over 2. Okay? And then plus the constant e times dx. So in this case, what would that give us here? Yep, e to the x, e times x. Okay? So at the end of the day, we have x to the e plus 1 over e plus 1 plus e to the x plus e times x squared over 2 plus e times x. And then remember, what's the last thing we need? Plus c. Good. Remember, make sure you do not forget that. Okay? So that's example A. So at first, it definitely looks daunting because we have a bunch of terms that look similar to each other. But if you just sort of break things down as, just break it down into each individual term, look at it as it stands and say, all right, which antiderivative rule do I need to work with here? That helps us get the antiderivative of each individual term. Once I see that, I just apply the rules as I see them and then move from there. So that's part A. So any questions on that part? All right. So moving on to part B from this. So it looks like we have another daunting one. So we have cotangent times cosecant minus sine minus cosecant squared. So with this one, it doesn't really look like there's a good antiderivative rule that lets us work with this product explicitly. So the next best thing would probably be to, just distribute the cotangent into both terms and see what happens. So let's go ahead and do that. So we have cotangent of x times cosecant of x minus cotangent of x times sine of x minus cosecant squared times dx. All right. So now, as before, let's go ahead and focus on the integral of each individual term here. So if we do that, we say, all right, we have the integral of cotangent of x times cosecant of x, okay, and then minus the integral of cotangent of x times sine of x minus the integral of cosecant squared of x dx. Okay? So in this case, it looks like we're going to need to deal with the integrals of trigonometric functions here. So if we take a look at the table that we've got, it seems to say, all right, well, we have the integral of cosecant times cotangent, as well as the integral of cosecant squared. But here's the kicker. If we take a look at this, it doesn't really seem like we have anything for cotangent times sine. So it seems like we're going to need to figure out some way to simplify this. So do you guys have any thoughts on how we could do that here? Any thoughts, comments, or suggestions? Okay. So here, go ahead.
So cotangent is cosine over sine.
Yep, that's what I was looking for. Good. So remember, cotangent of x is equal to, if you recall, that's just cosine of x over sine of x, right? So then that should pretty quickly tell you that cotangent of x times sine of x, if we just multiply sine of x to both sides, that's just cosine of x, right? So, as a result of this, we can rewrite the second term as, so cotangent of x times cosecant. Okay, cosecant of x dx, then minus the integral of cosine of x dx, then minus the integral of cosecant squared of x dx. Okay? So then, now that we have all that, let's go ahead and find the antiderivative of this. So as we established, we have cosecant times cotangent, which is just negative cosecant of x. Okay, we have that. And then minus, well, the antiderivative of cosine of x, which we established to be sine of x above here. So we have integral of cosine of x is sine of x. Okay, and then minus the integral of cosecant squared, which is just negative cotangent of x. Okay. And then once we have all that, then we add plus c to this at the end of the day. So remember, in this case, with problems like this where we have multiple terms, we can just focus on the just antiderivative of each one of them and then add plus c at the end of the day. So just one thing to keep in mind with that. Okay. So then as a result of this, well, we have minus the negative here, so these two cancel out. So ultimately, we're just left with negative cosecant of x minus sine of x plus cotangent of x plus c. Okay? So that takes care of that one. So like I said, another one that looks relatively daunting at first, but once you, break stuff down, try and simplify as much as possible, and then look at your table of antiderivatives, then it makes things a lot clearer what you need to do. Okay? So any questions on part B? So now let's take a look at part C here. So here what we have is, let's see. All right. So here what we have is x to the fourth plus the square root of x, all divided by 3x. So with this one, it doesn't really look like there's any way to properly deal with a quotient of a function yet, in terms of finding its antiderivative. So in this case, it looks like we're going to have to do as much as we can to simplify first, then do our antidifferentiation work from that. So in this case, what would be a good first step to simplify this? So here we have 3x is a common denominator of both x to the fourth and square root of x, right? So what we can do is say we can rewrite this as x to the fourth over 3x plus the square root of x over 3x dx, right? Okay, so from this we can say, all right, how do we break this off? So this is just the integral of, well, let's see. If we simplify each term as much as possible, well, what should we end up with here? So the first term should simplify as what? X cubed over 3, good. Whereas the second term simplifies to what? Go ahead.
Is it 1 over 3 root x?
Yeah, so 1 over 3 times the square root of x, or equivalently, that's the same thing as x to the what power? Over 3. Negative 1 half, right. Right, just applying our good old exponential laws here. Okay? So we have that, and then dx. So then from here we can say, all right, well, let's go ahead and split off each. Let's focus on term-by-term integration from that. So we have x cubed over 3 dx plus the integral of x to the negative 1 half over 3 dx. Okay? And then because we have constants here, we can just sort of throw those out of the integral. So we have 1/3 times the integral of x cubed dx plus 1/3 times the integral of x to the negative 1 half dx. Okay? So now from this, if we apply the antiderivative power rules, since we have, something of the form x to the n for both terms, so we say, all right, well, if we apply the antiderivative power rule, what's the antiderivative of x cubed going to be?
X to the 4th over 4.
Yep, x to the 4th over 4. Okay, so that's the first term. And then plus 1. Sorry, 1 second. Pencil's acting out. My bad. Okay, then what about this next term? So we have x to the negative 1 half. So if we apply the antiderivative power rule to this, what's going to happen?
X to the 1 half over 1 half.
Right, because if we apply the power rule to this, we have x to the negative 1 half plus 1 over negative 1 half plus 1. And that's all the terms we have. So then at this point we have to add what term? Plus c. Good. Okay. So what we have here is that the first term is just x to the 4th over 12. Nothing crazy with that. And then we have plus 1/3 times x to the, well, let's see, as you said, negative 1 half plus 1. That's just positive 1 half. And then you would also have positive 1 half downstairs. And then plus c. Okay, so now, how does this simplify? So this equals, let's see. So we have x to the 4th over 12 plus, let's see. What would this term simplify to? So we have x to the 1 half times what constant? What's that?
Yeah.
Not quite. So remember, if you recall, we have 1 over 1 half. If you want to divide by a fraction, that's the same thing as multiplying by reciprocal, right? So as a result of this, if you have 1/3 times 1 over a half, that's the same thing as saying, all right, we have 1/3 times the reciprocal of this, which ends up being 2 over 1. So this is just 2/3. Okay? So we have 2/3 times x to the 1 half plus c. So this is our final answer. Okay, so any questions on any of this? Okay, so let's see. What I'm going to do for now is say, all right, well, I have 2 more examples planned. I got about 10 minutes, so why don't we take about 5, I'll take about 5 minutes to do, I'll give you guys a couple minutes to do each of the problems on the back here. And then we'll reconvene in about 5 minutes. And then also for those watching online, you can also skip to 5 minutes later once you finish these. So. Okay, let's go ahead and reconvene. So, looking first at part A, so we have the integral of x plus 3 quantity squared dx. So the hint was to first expand the function inside the integral. So if we do that, we say, all right, well, x plus 3 quantity squared, if we expand this out, is equal to what?
X squared plus 6x.
Yep. So x squared plus 6x plus 9. Okay. And then dx. Okay. So then if we focus on each individual term and then take out the constant as necessary, we should have x squared times x squared dx plus the integral of, well, I should say 6 times the integral of x dx, then plus the integral of 9 dx. Okay. So then if we integrate each of these using the antiderivative power rule, we should end up with what as our antiderivative here?
X cubed over 3 plus 3x squared plus 9x.
Yep. Yep. Because here we have 6 times x squared over 2, and then plus 9x, and then of course plus c. But the nice thing is that 6 over 2, well, that just becomes 3, as you said. So we have x cubed over 3 plus 3x squared, and then plus 9x, and then plus c. So that's part A, no problem. Then what about part B? So if we do a similar thing where we break off as each individual term and then get rid of and throw out the constants as needed, we have 5 times the integral of 1 over x dx minus pi times the integral of sine of x dx. Okay? So then using the necessary derivative rules, we have that this is equal to 5 times, so as we mentioned, 1 over x had antiderivative equal to, what's that?
Log of x.
Yeah, natural log of absolute value of x, right? Yeah, make sure not to forget the absolute value of x here either. Okay, and then what would be the antiderivative of this term?
Plus pi cosine x.
Right, because we have negative pi times negative cosine of x for the antiderivative here, and then of course here plus c. So then what happens is that if we cancel out the two negatives, we end up with 5 times natural log of the absolute value of x plus pi times cosine of x, then plus c. All right. Okay, and that's all I have for today. So, any questions on any of that? Okay, cool. Well, then I will see you guys on Friday, because remember, no class because of that reading day on Wednesday. So otherwise, I'll see y'all on Friday.
Quizzes this week?
One on Friday.
Okay.
And also as a quick reminder, because of the reading day, the homework for this lesson will also be due on Friday as well.
Can you go back to the
First page? Yep. Where are you at? There you are.